In 1988, the Morris worm stalled the early internet. In 2003, the Slammer worm compromised 75,000 servers in 10 minutes. These events shared a single point of entry, a buffer overflow, a programming error letting attackers seize root access to a secure system. The mechanism of this exploit is a matter of volume. An attacker sends a program more data than its designated memory container can hold. The excess data spills out, overwrites the CPU's instruction pointer, and hijacks the execution flow of the machine. Modern operating systems now use hardware-level defenses intended to stop this exact attack, yet enterprise environments are still compromised using the same underlying vulnerability. We are going to trace the evolution of this memory arms race. We will start with the mechanics of the classic stack smash, observe how modern defenses stop it, and reveal how return-oriented programming weaponizes the system's own libraries to execute a payload.
Understanding this architectural flaw is mandatory. Decades of additions to the operating system have failed to eliminate the architectural opening created by memory corruption. This diagram outlines the macro architecture of system memory. While regions like the text and heap handle code and dynamic data, we need to focus entirely on this specific region, the stack. The stack acts as the CPU's short-term scratchpad. It dynamically allocates temporary space for local variables and manages the execution flow of active functions. Data here is stored in a strict sequential manner. When a program needs memory, the system stacks blocks of data directly adjacent to one another. This dual-purpose design creates an inherent risk. The system stores untrusted user data immediately next to critical execution instructions. Consider a standard C function that accepts user input. If the programmer accepts that input without verifying its exact byte size, a practice known as bounds checking, they leave the application vulnerable. This maps the function's stack frame. The system builds 3 blocks, a local buffer at the top, a base pointer in the middle, and the return address at the bottom. The return address is the CPU's navigator, telling the processor where to resume. In safe execution, standard input flows in as hexadecimal data, fitting inside the local buffer. The base pointer and return address remain untouched. But C trusts the user input. It does not actively check if the incoming data fits the container. It simply writes the bytes sequentially into memory until the input stops. An attacker exploits this by feeding the program a massive string of data, scaled to be much larger than the local buffer. The data spills past the buffer's border, overwriting the base pointer and continuing directly into the return address block.
This payload reaches the return address at a calculated byte. The attacker writes an address that redirects the pointer back up into the buffer, triggering a hidden payload of executable shellcode. When the function terminates, the CPU reads the corrupted return address and jumps directly to the attacker's instructions. By overriding a single navigational variable, the attacker successfully forces the CPU to execute foreign code. To stop this, microprocessor engineers built executable space protection into the hardware. It is enforced using the NX, or never execute bit. This bit enforces write X or execute. A memory sector holds writable data or executable code, never both. The stack is now tagged as data only. In a stack smash attempt, the CPU jumps to the shellcode, but the hardware recognizes the NX bit and execution halts, triggering a segmentation fault.
Segregating code from data neutralized the classic exploit. However, this defense relies on the assumption that an attacker must inject their own code to take control of a process. Return-oriented programming bypasses executable space protection by abandoning code injection. Since the attacker cannot run foreign code, they must hijack code that is already trusted and loaded in memory. The primary target is the standard C library, libc. Because the operating system requires it, libc is loaded into executable memory, containing thousands of legitimate instruction sequences. Attackers mine this library for gadgets. A gadget is a tiny fragment of assembly code performing a simple action ending with a return instruction, hex byte C3. This return instruction mechanically reads the memory address at the top of the stack pointer, jumps to it, and increments the pointer by 8 bytes. By realizing the return instruction blindly follows the stack pointer, attackers can turn the stack into an indirect instruction pointer. By lining up specific memory addresses, they orchestrate an entirely new program out of existing scraps of code. Exploiting modern 64-bit Linux requires an extra step. Modern 64-bit architecture requires system call arguments to be passed inside hardware registers, specifically the RDI register, rather than on the stack. To spawn a shell, the attacker must force the address of the text string /bin/sh into the RDI register, then trigger the system.library function. This 64-bit ROP payload contains 0 executable code. It stacks padding, the address of a POP RDI gadget, the string /bin/sh, and the system function. When the vulnerable function returns, it pops the first address, jumping to the POP RDI gadget in libc. This instruction pops the string pointer address, sliding it directly into the RDI hardware register. The gadget hits its return, popping the final address and jumping to execute the system function with the RDI register primed. Without executing a single byte of untrusted data in the stack, the attacker chained legitimate memory addresses together to simulate a program and spawn a root shell. The stack has become a physical sequencing mechanism. Like a player piano roll, these static data points dictate the complex striking of the CPU's logic. Attackers achieve Turing-complete execution entirely through data formatting. This rendering of the NX bit as ineffective demonstrates that data and code are functionally interchangeable. By treating memory addresses as instructions, ROP exploits a structural truth. In a stored program computer, there is no physical difference between the data being processed and the code doing the processing. This makes executable space protection an incomplete defense. It attempts to separate code and data in a system where they are, by design, the same thing. The modern industry response is address space layout randomization, or ASLR. It randomizes where libc lives in memory every time a program runs, making it difficult for attackers to predict gadget addresses. ASLR relies entirely on secrecy. If an attacker can trigger a memory leak to reveal a single function address, they can calculate the offsets for every other gadget and bypass the randomization. Layered protections like NX and ASLR make exploitation more technically demanding, but they do not address the vulnerability that allows data to overwrite the return address. The only definitive solution for memory exploitation is secure programming at the source. Implementing strict bounds checking eliminates the buffer overflow vulnerability before compiling.